back again, and today we're going to be calculating the pH of bases, which is slightly different than what we've been doing before. So, some things you should know. Let's start with strong bases. Strong bases are exactly like strong acids in that they 100% dissociate. So whatever the concentration is of your base, that's what it'll break apart into concentration-wise in water. Also, I'd like to remind you of one strong CalBar. Those are the only strong bases. So anything group 1, strontium, calcium, or barium, those are the only ones that are considered strong bases. So the majority of all the bases we're going to be dealing with are going to be weak bases, which we're going to handle a little bit differently, but strong bases are super easy to deal with. Let's try one. So if you take a look at this, it says, what is the pH of 200 milliliters of 0.100 molar NaOH? The milliliters here makes zero difference. We don't care about the milliliters. It doesn't matter to us. What we do care about is the 0.10 molar NaOH. Now, if you take a look at the NaOH will 100% break apart into Na plus and OH minus. 100%. Completely break apart. Now, if we were to do ice, there's not really an ice involved. There's just an initial and a final. We start off with 0.100 molar of this, and we have none of either of those two things. At the end, we have none of this, and we have 0.100 molar of this and 0.100 molar of this. Now, the question asks, what is the pH? Now, the only thing we're really caring about here is the OH minus. Now, we know that at the end, we're going to have 0.100 molar OH, right? So, as ugly as this is, we don't care about Na plus at all because it doesn't help us in our quest to get to pH. What I can do, if you think about it from before, is I can take the P of OH, which is the same as negative log of my OH, right, concentration. And if I do that, I'm going to end up with the negative log of 0.100. Now, for those of you who are mathophiles, that's going to be really straightforward because the PaOH is going to equal to 1. But that's not what the problem's asking. The problem is asking what is the pH. Let me remind you of this truth. pH plus POH is equal to 14. So if we work backwards from that, and incidentally, this is incorrect significant figures because if you take a look, we had 3 significant figures in our problem, which means our log of this has to have 3 significant figures as well. And remember, for both POH and pH, the significant figures are counted after the decimal. So we have 3 here because there are 3 here. Which means if I'm subtracting from 14, I'm going to end up with a POH of exactly 13.000. Again, these are the only 3 numbers that matter. Now, what about weak bases? In fact, as I said before, the majority of bases are actually weak bases. And what we know is that when we throw a base into water and it's a weak base, very little of it dissociates. In fact, whenever we're doing any equilibrium, acid or base or anything, our mantra is always throw it into water and see what happens. What you need to know when you're dealing with either a weak base or weak acid is you need to know either the Ka or Kb. So in this case, we are going to be dealing with weak bases, so we need to know what the Kb is. When we're solving for our ice tables, remember, we're solving for X, and X in all those cases equals OH minus concentration, which is not H plus. Additionally, when we take the negative log of OH, we're going to get POH, just like we did in the previous problem, and if we subtract from 14, that's the way that we're going to get our pH of a problem. The best way to deal with this is to just try a problem. So let's do this here, but the biggest thing I want to start you off with here is that we need to write what the equation is that we're going to be working with. Now, we have NH3, right? That's what we're working with. And our NH3, what do we do with it? Well, we throw it into water. So we take NH3 and we throw it into H2O, right? When we do that, we're going to have an equilibrium. And this NH3, which is acting as a base, is going to snag a hydrogen off of this, because that's what bases do, right? And it's going to end up with NH4 plus OH minus. Now you need to be careful because they love using things like H3s or NH2 or whatever because we see H's and we think acid, and this is one of their tricks. This actually is something, and ammonia is one they use often. You see how on this side it has one less hydrogen than here, which means this is its base and this is its conjugate acid. Now if I'm doing an ice table, which I'm always going to do, I'm going to write I, C, E, and my initial amount that I'm going to start off with here, and again, they throw off kind of the weird, like, trying to get you off here, but this 300 milliliters is not useful to us at all in this problem. What we do care about is the 1 molar right here, yeah? So we're gonna start off and we're gonna go, all right, we have 1.0 molar of this, right? We don't care about liquids, right? So there's nothing to deal with here, and we have none of these two things. Later on, we're gonna deal with things that exist over there, but not for right now. My change, since it's a 1 to 1 to 1 ratio, I'm gonna lose x here, I'm gonna gain x here, and I'm gonna gain x here. And at the end, I'm gonna end up with 1.00 minus x, x, and x. Now, one of the things that I like doing early on in a problem, I did not do it at the start of this, I'm doing a different color here, is I like writing my K expression from my reaction. So if I take a look at this, and I'm covering it up right now, but can you see that we have NH4 plus and OH minus are on the product side, and NH3 is on the reactant side. So my KB in this problem is going to be equal to my NH4 plus times my OH minus all over my NH3 concentration. And all of that is going to be equal to 1.8 times 10 to the negative 5. Now, if I take a look down here and I take all my equilibrium values, I'm going to plug those back into my equation. And if I do that, I'm going to end up with x times x on the top all over 1.00 minus x on the bottom. And all of that's going to be equal to 1.8 times 10 to the negative 5. Now, for those of you who love polynomials, you could look at this and go, all right, I'm going to polynomial the heck out of that. But we have a trick here. Whenever we have a very small k, which is what we have right here, negative 5, we can make the assumption that the amount that's being lost here in our x is so small compared to the original that it's negligible. It's the mosquito on the elephant concept. So what we can do is we can get rid of this by saying 5% rule. Now, if you take a look at it, my students in previous years have called this the dead frog because you see the eyes and the mouth and the tongue sticking out. So they often will say dead frog it. You don't have to do that. It's free of charge there. But when we do the math on this here, won't we be multiplying this 1 by this 1.8 times 10 to the negative 5? So our x is going to be equal to 1.8 times 10 to the negative 5. Our x squared, sorry. When we square root this 1.8 times 10 to the negative 5, right, because we want to get our x by itself, we end up with an x value that is equal to, let me take a look at my math here that I already did, is going to be equal to 0.00424. Now, if you just leave that there and you don't do anything more with it, and you're like, hooray for me, I've done the problem right, your grader's going to hammer you because we need to acknowledge that this x value, isn't it the amount of NH4 plus and the amount of OH minus? But we don't care about the NH4. We are dead to us. What we care about is this guy, the OH minus. So somewhere in here, you need to make the relationship that OH minus is equal to that 0.00424. Now, the question asks for the negative, for the pH, right? Now, the thing that we're tucking in is we know that when we do a math here, that 14 is equal to my pH plus POH. Now, I can figure out my POH by taking the negative log of that number that we have over here, the 0.00424, and that's going to be my POH. And then I can subtract that from my 14. So in this case, when I take the negative log of that, I end up with 2.37 is my POH. Now, there's a lot of significant figures here. The reason I ended up using only 2 right here is because in the problem, I used 1.8 as part of my math, and that only has 2 significant figures, and I'm only allowed to have 2 in my final answer. If I were just starting with this problem, there's 4 significant figures here. I'd have to go 2.37 and then write down whatever the other number was. To finish the problem off, though, I have to go 14, subtract my 2.37, and that's going to give me my pH. And if you do that math, then you're going to end up with pH is equal to 11.63. And again, I want you to note the 2 significant figures that we're using. Now I want to look at a really, really important equation here. Now we may have remembered Kw from the fact that Kw is equal to H plus concentration times OH minus concentration is equal to 1.0 times 10 to the negative 14. The other thing that's true is that Kw is equal to Ka times Kb. Now I want to make a couple points here about the Ka and Kb that are incredibly important. Whenever you have a Ka value, that K is a result of you throwing an acid into water. The Kb is when you throw this acid's conjugate base into water. So you can relate these two things together, which means this. If you ever have two conjugates, an acid and a base, and they only give you one of the values, let's say they only give you the value for Ka, right? You can then divide into 1.0 times 10 to the negative 14 to get your Kb. So there's information that you can glean even if it's not given to you right away. So let's try a problem. So when I take a look at this right now, I have this very scary phenylammonium ion, C6H5 NH3+, which by the way, cations tend to be acids and anions tend to be bases, just that something that we'll talk about that a little bit more. But I give you the Ka of 2.6 times 10 to the negative 5, and I'm asking for the conjugate of aniline. Now if you take a look at these two right here, the only difference between these two is that this has one less hydrogen than this does. So aren't they a conjugate acid-base pair? So if I know what the Ka is for this, right, couldn't I then divide that into 1.0 times 10 to the negative 14 and get what our Kb is? Now, we have this table that you can look at, and if you take a look here, it actually gives you the Kb for this, so I don't have to do the math, but I could have taken the 2.6 times 10 to the negative 5 and divided it by 1.0, divided into 1.0, and could have gotten that number right there. So let's try this monstrously hard problem. And again, this may seem really scary to you, but the reality is that it doesn't matter what this really long thing is. So see how it gives us phenylammonium ion, and then they give us aniline? Well, we're working with aniline right now, and that's a base. So what do we do with everything all the time? Throw it into water, right? So we're gonna take our aniline and we're gonna throw it into water. Now I'm gonna do this, and it's gonna seem really weird for you to do this, but I'm gonna make aniline just AN, right? I'm gonna throw that into water. And when I do that, since it's a base, what is this aniline going to do? It's gonna grab a hydrogen from this water. So what is it gonna make it? It's gonna make it ANH plus, because that hydrogen comes over and makes it a positively charged compound. And we end up with OH minus. Now, if you feel more comfortable doing it this way, you can write out, instead of this, you can write out C6H5NH2. That is this. Now, on the AP exam, I might do that just because I don't want the grader to think I don't know what I'm doing. But this is how I would write this out. Now, we're gonna do our typical ICE problem, ICE, right? Now, they give us in the problem 0.350 molar aniline. They also give us 500 milliliters. Again, that's a distractor. We don't need it for this type of problem. Later on, when we want to figure out moles, we can always go milliliters times molarity and end up with millimoles and then convert to moles, but we'll deal with that when we deal with titrations next. So I'm gonna do my ICE problem, and they give us 0.350 molar of the aniline. This again is dead to us, and we have none of these two things to start. What's the change gonna be? And again, it's 1 to 1 to 1. Don't always assume that it's gonna be 1 to 1 to 1, because it might not, right? And then at the end, we're gonna end up with 0.350 minus x, and here we end up with x and x. And just like before, what we're gonna do is we're gonna plug that all into the equation, the Kb equation for this. So I'm gonna write Kb up here, and my Kb is gonna be equal to the concentration of NH plus times OH minus all over the concentration of N. Now, one of the things that I didn't do here, and although I showed it to you, I'm gonna do it up in this space right here, is remember we said our Kw is equal to Ka times Kb, and even though I gave you the table up there, since this is 1.0 times 10 to the negative 14, what I could do is I could plug in my Ka value into here, and when I do this 2.6 times 10 to the negative 5, and I solve for my Kb value is gonna end up being 3.8 times 10 to the negative 10. This is an incredibly important thing that you do not use your Ka for this spot. So I'm just gonna write this as my 3.8 times 10 to the negative 10. And that's gonna be equal to these values that I'm plugging back into here. So I'm gonna go x on the top, all over 0.350 minus x. And I'm hoping you're seeing something here. If it's a 1-to-1 ratio, you can very quickly rearrange this equation so it's going to be 3.8 times 10 to the negative 10 times 0.350 all on this side, right? And isn't that going to be equal to x squared? And then what we can do is if we want to get rid of the x squared, we can square root both sides, and that will give us our x value. Now, I happen to have done this in advance, and I end up with 1.15 times 10 to the negative 5. That's our x value. Now, just writing that as our x value is not good enough. We have to then let everyone know that that's equal to our OH minus. Now, it's also equal to our ANH plus because they're both equal to x, but we only care about our OH minus. And again, once you have your OH minus concentration, it's exactly the same in every problem. What you're going to do is you're going to take your negative log of your OH minus, right, is going to give you your POH. And when you do it in this particular case, your negative log of this is going to give you 4.939 as your POH, which you can then subtract from 14, and you end up with your pH equal to 9.06. Now you may be thinking, well, why did you do 9.06 here when you had three significant figures here? Well, going back to our original problem, I used three significant figures here, but I used two significant figures originally, 2.6 to do the math. So in reality, I should only have two significant figures right here. Now, as I go behind all this mess here, the more we do these, the better off you're going to be. But this has been our intro to this. Hopefully it's been helpful. I'll see you in class.